In this lesson, we're going to investigate equilibrium. We're going to define dynamic and static equilibrium. We're going to look at a few different types of equilibrium, and we're going to get into stability and this concept of center of gravity. So let's start by defining equilibrium. A system is in equilibrium when there is no acceleration. Recall, accelerations are caused by forces, and the net force and the acceleration will be in the same direction. So if a system is at rest and is remaining at rest, it's in static equilibrium because all the forces are balanced and there's no motion. If an object is in motion, we say the system is in dynamic equilibrium. So if the acceleration is zero, the system is either at rest or moving with a constant velocity, and it's in a state of equilibrium. But we've got to be careful with this, right? Because it is true that net force equals mass times acceleration. So if there's no acceleration, there's no net force, but there's going to be another condition necessary. So the first condition of equilibrium is simply that. The net force must be zero. That has to be true for the acceleration to be zero. But that's not enough. It's necessary for equilibrium that the net force be zero, but it's not sufficient. Because if we look at this is a hockey stick laying on ice, and we're looking down on it from the top. If we push here to the right and we push here to the left with an equal amount of force, the sum of those forces will be zero because the two forces act with same force, opposite direction. So it is true that the net force is equal to zero. And this hockey stick won't undergo any net displacement, but it will start to rotate around a center in between these two things, which is a type of acceleration. We have angular acceleration. So it's not enough for just the net force to be zero, but it must also be true that the net torque must be zero. So not only must the net force be zero, the net torque must also be zero. So the conditions for equilibrium, net force equals zero, net torque equals zero. If those two things are met, then our system is in equilibrium. And if it's at rest, then it's in static equilibrium. If it's in motion, it's in dynamic equilibrium. We're going to consider mostly things in static equilibrium. At rest, net force zero, net torque zero. No acceleration, no angular acceleration. Now, just because something is in equilibrium does not mean it's stable. Stability is achieved only when the center of mass is going to return to a stable position if some other force acts on it. So if you have a hanging pendulum, right, then it's fastened up here, and it's going to naturally hang down here at its lowest point. If something displaces it to the side, then this pendulum comes up over here, and what we end up with is tension in the string and gravity straight down. And that tension actually has a component to the right, which is going to cause this thing to swing back towards where it came from. So it's got a restoring force that tends to return it to its equilibrium position where the net force is zero and it doesn't accelerate. Or if you had a bowl with a marble in it, down here the marble's in stable equilibrium. If it gets displaced either side, then gravity is going to pull it down the hill and it's going to return back to its stable spot. So stable equilibrium means any displacement from equilibrium, there's going to be a natural force that acts to return it back to its stable position. Unstable equilibrium, not so much. In fact, it's just the opposite. In unstable equilibrium, if it's displaced from where it's balanced, then it's going to fall over. So here we have a pencil balanced on its very tip, and you'll notice this is be very hard to do. You got to get all the weight centered just above that tip, so that there are no net forces or net torques, and the whole thing adds up to zero. If this gets disturbed even just a little bit, it's going to fall over, because as soon as it's disturbed, right, here's where this used to be. Now our center of mass, or our center of gravity, which I'll talk about in a minute, is over here, and that essentially exerts a torque. Right now it's got a force and a lever arm, and this is a non-zero angle, and so this is actually going to cause rotation, and it's going to fall over. So even though the normal force and weight still balance, there is a net torque here. This is unstable equilibrium. We could do the same thing if we put that marble on a bowl that was upside down. It could balance right there, but as soon as it gets displaced either way, it's going to be pulled even further away from equilibrium. So stable equilibrium, it wants to return to a stable state. Unstable equilibrium, it's going to just progress farther from its stable state. And then of course there's neutral equilibrium, which means it doesn't really care. If it gets displaced, woo, it's not going to get returned to where it was, but it's also not going to become less stable than it used to be, or proceed in that displaced direction. So if we had a marble on a flat surface, then we have neutral equilibrium. So stability depends on kind of the location of the center of gravity compared to its support. And we're going to take a look at that, but let's look at this center of gravity that I mentioned. Center of gravity is the spot that acts as though all the gravitational forces act through it. So consider, if you will, a meter stick. Where would you put your hand to balance it? Well, you'd put it right under the middle, because every section of this meter stick has weight, and so you have to supply an upward force equal to the total of that weight, but by putting your hand up in the middle, all these forces over here are going to cause torque this way, all these forces over here are going to cause an equal torque that way, and so the net torque is 0. So if you find the center of gravity of something, you find where it will balance and where the gravitational torques will end up being 0, because they exactly cancel out in all directions. Now, this is also called center of mass. The two are identical as long as we're in a uniform gravitational field. That's all we'll deal with. So center of mass, center of gravity, for our intents and purposes, they're the same thing. And it is the point that acts as though all the forces due to gravity are acting through it. So when we were looking at this picture a minute ago, and we had the center of gravity over here, that's where the weight force acts. So center of gravity is where we can put the one point on our extended body, on our big system, where we can say gravity is acting. And the center of gravity for different shapes is in different places. For a circle, it's right in the center. So like if you had a hula hoop, you couldn't actually find a spot to balance it, at least horizontally. You would have to just tie like strings across it, because its center of mass, its center of gravity, is where there's no mass at all. If you have a rectangle, then the center of mass is just where the diagonals intersect. If you have a triangle, then it's the medians. So you'd go from the angle from the vertex to side opposite, so bisects that side, and where two medians intersect, that's the centroid. That's the center of mass for the system. For an irregularly shaped object, you can actually determine where its center of mass would be. If you suspended it by a string, and so this thing was hanging here off of a string, then it would hang straight so that its center of mass would be right underneath it. Because if its center of mass was over here, then there'd be a torque to put it over into equilibrium. So its center of mass will hang right below this string, and so if you copy a line straight down from the string, that line's going to go right through its center of mass. Then you could suspend this thing from another string and find where the two lines intersect, and you would get its center of mass. So you can find the center of gravity for oddly shaped objects. We're basically only going to deal with rectangles and uniform objects where their center of mass is basically their centroid.